We can start.
Yeah, okay. People are coming in. Okay. Yeah, let's start. To begin with, I want to clarify about the place where I got confused last time. So remember, I was trying to show that on A tilde, in case you do not remember what A tilde is, let us go back one more. That's A tilde. This is in the proof of Egorov's theorem. So that's A tilde. I want to show that the convergence is uniform on A tilde. So that means given any delta, I have to show that mod fjx minus fx is less than delta for every x in A tilde for large j. Meaning we have to, given a delta, we need to find an integer so that whenever j is greater than that integer, mod fjx minus fx is less than delta for every x in A tilde. Now, given a delta, choose an n such that 1 by n is less than delta. We can always do that. Now, I'm making a change here. I've already posted the notes. If you want, I can post this revised notes again. I'll take this n greater than n. I can always do that, right? That is the change. I mean, delta could be such that 1 by n is less than delta even for a small n. But if I take a bigger n, I mean, I'm only getting better. That's what. 1 by n will still remain less than delta. Now, for any x in A tilde is the intersection, mind you. So every x in A tilde is in this ENKN for this particular n. And the moment x is in ENKN, mod fjx minus fx is less than delta for every j greater than kn. And hence we are done. That's it. That was the only little change that I made here. Okay. Any question? If you have any question, ask now. Okay. If not, we have done. Okay, maybe I just show the end of the slide. This was the end of the proof of Lusin's theorem. By Lusin's, I mean, we wanted to do these things because I wanted to show that every measurable function is all nearly a continuous function. Continuous functions are of great use. Okay, maybe today I should start with what should we start with? Oh, by the way, that clarification in Egorov's theorem was due to Sushil. I asked Sushil why I'm getting confused, and he just pointed this out. Okay, now that we know these things, let's see this. CCX is dense in LP mu. Remember, there are some things I'm not always stating, but maybe at the beginning of today's class again, I shall remind everyone that X now is a locally compact topological space. What else? Yeah. And mu is a regular Borel measure. Measure on the Borel sigma field, and regular means you can approximate any measurable set in measure from outside by open sets and from inside by compact sets. This all happened for Lebesgue measure of the of Rn on Rn. Okay. recall that we showed that simple functions are dense. I mean, subject to some qualification, simple functions. Okay. So you remember that result? Should I go back and kind of show you that? It was somewhere here. Yes. I'm referring to this. So consider all simple functions that x, the set of all x with where Sx is non-zero, has finite measure. If that has infinite measure, then you are in trouble. It may not be that such functions may not be in LP. If they are finite measures, certainly in LP. Simple functions, okay? So I'll use this result. So since simple functions are dense, it is enough it suffices to show that every indicator function say IE for needless to say measurable E, but more importantly mu E finite, that is the kind of simple functions which are dense. That is the kind of simple functions which are dense are all of the form summation Ci indicator Ei I equal to 1 to n for some finite number n, where Ei's are a finite measure. Ci is a non-zero. Okay. So if I take a measurable set of finite measure, I take the indicator function on that. If I can approximate that by CCX, then we are done. Because linear combination of these things are dense. Can be LP approximated. I want to remember that when I talk of approximation here, I mean LP approximated. That means okay, it can be LP approximated by a sequence Fj from C6. So this means I need to find a sequence Fj from C6 such that the indicator E minus Fj LP norm goes to 0. LP norm with respect to this measure mu. This is a very general result. Mu is any regular Borel measure. Okay. Now, how do you even think of a proof of such a thing? Well, you have to use the local compactness of the topological space X. What does the local compactness tell you? The local compactness is the most important corollary, I think, the most important consequence of having a locally compact topological space is Urysohn's lemma. Are you familiar with Urysohn's lemma? I need an yes, no answer.
Yes, sir.
Okay. Okay, good. Now, also I have mu to a regular Borel measure. Look at the top line. Now, regular Borel measure means that this set E, whichever I have, a finite set of finite measure. So by regularity of mu, get a sequence of open sets, say Gj, such that what? First of all, E is contained in each Gj, and mu Gj, oops, decreases to mu E. Now this can be done because one of the properties of regular measure is for any measurable set mu E, any measurable set E, mu E is equal to infimum over mu V, such that V contains E and V are open. In the moment you have infimum, you have a sequence decreasing to the infimum. That's all. Okay. Similarly, again, property of regularity. Get a sequence of compact sets Kj such that this time each Kj is contained in E and mu Kj increases to mu E. Not in your measure theory classes, these have been constructed. Such regular measures have been constructed actually on the Borel sigma field of a locally compact topological space X. Okay. Now, the situation is this: Kj contained in E, contained in Gj. The Kj's, and as J becomes large, these are shrinking. Kj's are approaching E from inside, Gj's are approaching E from outside. So the gap between them is shrinking as J becomes large. Oh, one more thing. Very importantly, also mu G1 is less than infinity. Why? Anyone has an answer why mu G1 should be infinity? No one no one with an answer? Is anyone listening? Okay, I'm not sure whether anyone is listening whatsoever. Okay, mu G1 is finite because mu E is finite, and that's the limit of the sequence of mu Gj's. So sooner or later, I mean, you can start with the mu G1 infinite, but obviously if the sequence mu Gj has to decrease to a finite number, then sooner or later they will start becoming finite. You can have some infinities in the beginning, throw them away. They're of no use. That's right. Okay. All right. By Urysohn's lemma, now there exists phi j in CCX, that is continuous function with compact support. This is the great advantage in locally compact spaces, local compactness, such that on Kj phi j is 1. So you look at this containment, Kj contained in E, contained in Gj. Urysohn's lemma precisely tells you that there is a continuous function with compact support, such that on Kj it's 1. Then it decreases to 0 outside Gj. So support is contained in Gj. On entire X. So for every X, 0 less than equal to phi j less than equal to 1. 0 less than equal to phi j X less than equal to 1. Okay.
Okay, sir.
Yeah. Since now note that phi j's are dominated by indicator function of G1. I mean, phi j is less than equal to indicator function of Gj because support phi j is contained in Gj and phi j's never exceed 1. So phi j is dominated by indicator function of Gj and Gj is contained in G1. Gi's are decreasing. So each phi j is dominated by this. Is indicated G1 integrable? The answer is yes, because G1 has finite measure, otherwise problem. And indicated G1 is integrable. So integrate G1 with respect to d mu, we will get mu of G1, which is finite. And phi j's go to indicated E pointwise. Why? Well, take any point x. It's either in E or not in E. If it's not in E, it's outside E. And since GJs are decreasing to E, sooner or later this this point at this point phi jx will be 0, and indicator is 0. The other thing is, if it's inside well, I mean, I'm hand waving here a little bit. Provide the argument why. Okay, maybe this can be taken up in perhaps in the tutorial class, pointwise. It requires 3 minutes thinking, but please do that. By DCT, because you have pointwise convergence and dominated by a function which is integrable, phi j converges to indicated E in LP. That is, phi j minus indicated E at x goes to 0. So to the power p, phi j x minus indicated E at x to the power p also goes to 0. And the whole thing is dominated by whatever. I mean, phi j x minus indicated E to the power p will be dominated maybe by mod phi j to the power p plus indicated E to the power p. Indicated E to the power p is indicated E. Mod phi j x to the power p is dominated by, again, indicated G1. That's right. So what did we produce? Given an indicator, yeah.
By dominated convergence theorem, we say that integral over phi j tends to integral over 1 in.
Right. So that's why consider the sequence phi j minus indicated E.
Okay.
That pointwise goes to 0. And that will be dominated by 2 times indicator E or something like that. Okay. You actually need you need this. To show this, you need.
Okay, sir. Okay, sir.
You need this. Convergence of this to 0 is what is needed. So consider this sequence, okay? Call it, I don't know, GJ. GJs converge to 0 pointwise and are dominated by, as I said, maybe 2 times indicator E. Indicator G1, sorry. Dominated by 2 times indicator G1. Yeah. Yeah, good point, actually. So that GJs are converging to 0, and hence the integral will go to 0 if we can dominate GJs by an integrable function, which is the same as dominating phi j. Indicator E, of course, is less than equal to indicator G1. E is contained in G1. Okay, so given an indicator function, I have approximated it by a sequence of CCX functions. 2 inputs, one is regularity of the measure, the other is Urysohn's lemma. Both of these are consequences of local compactness, as you very well know now. Okay, so that's one thing. So CCX is dense. Maybe the next thing I should show you while we are at it is LP of Rn is separable. It's a question, right? Whether as a metric space this is separable or not. You need a countable dense subset. it's possible to do in Rn, and you will see why it is possible to do in Rn. So that will also give an idea on what kind of spaces it will fail. I mean, you you use the fact that Rn is separable, and other structures. That's not the only thing. Maybe for F in LP of Rn, first get G in CC, just what we proved above. LP in Rn and so given an epsilon positive, you first approximate F by a continuous function with compact support, and then we'll see. So this can always be done, right? I mean, we just proved that. Okay. Now this G is a continuous function with compact support. A compact set is closed and bounded. Now get a ball. I don't think it matters whether it is closed or open, but I may be wrong. Get a ball centered at 0 and of radius some m, such that support G is, I need a name for this ball. Okay. I mean, G is a, oops, what have I written? G is a function with compact support. So that support is a compact set. Since it's a bounded set, I can always put it in a big enough ball. And ball is not the only thing. You could take a box, a cube as well, but why not a ball? And what's perhaps slightly important is I want a ball of integer, positive integer radius. So I'll find a positive integer which is so big that the compact set support G fits inside the ball of radius. Okay, fine. Now I shall apply Weierstrass theorem, that you can approximate continuous functions by polynomials. Agreed? Get a polynomial. I normally write P for polynomial, but we have P for LP, so I'll call the polynomial xi. Get a polynomial xi such that xi approximates G, but in Weierstrass theorem, it's the sup norm. All right. Sup norm where? Well, you will only be interested on the support of G. So this sup norm is on the support of G, nothing more than that. Okay. Supremum mod Gx minus Xix as X runs over the support of G. I'll take that to be less than epsilon by 2 into the measure of this ball to the power 1 by Q, where Q is such that given a P, I can always find such a Q even if P equal to 1. Okay. All right. Now, so I found a polynomial xi. Okay, I should have written something more. Weierstrass theorem tells you that you can find a polynomial xi. I want a polynomial with rational coefficients. Again, this can always be done. Why? Because Weierstrass theorem is the crucial input that you can find a polynomial. The moment you have found a polynomial, you can find another polynomial close to it which has rational coefficients. So a polynomial xi maybe to begin with comes with arbitrary coefficients, rational, irrational, whatever. But if it has irrational coefficients, find rational numbers close to that, very close. And then you will be able to approximate the original polynomial xi by polynomials with rational coefficients to whatever amount of precision you want in the SUP norm. You can, by Weierstrass theorem, you can always get a polynomial xi with rational coefficients, which is close to this continuous function with compact support. Compact support is important, so that this SUP norm G minus xi does not get out of hand. I want it only on the support of G. Okay. Okay, now I compute I have to compute the G minus xi norm in LP, because finally my function f comes from LP and I have to approximate that in LP norm. I have found G epsilon by 2 close to f. I'm now trying to find, I'm trying to construct a separable set and find an element from there which will be epsilon by 2 close to G. So that finally G is epsilon by 2 close to F. That element that I shall produce is epsilon by 2 close to G. So that will be epsilon close to F. But all of this in P norm. Oops. Now this is less than equal to well, you will ask me why, and I need to give perhaps a little clarification there. Maybe before I write this, I do that. I call the polynomial xi tilde. Let xi be the measurable function which is equal to xi on Bm and 0 outside. So is equal to xi tilde, sorry. So I got a polynomial xi tilde with rational coefficients close to G. But polynomials are a problematic thing in Rn. If you integrate polynomial over whole of Rn, it will not be finite. So they are not there in LP. I mean, the simplest of polynomials, 1 is not there. I mean, for obvious reasons. So you need to chop it off. Fortunately, I'm approximating only G, which has compact support. Its support I have put in some large ball. So I don't care what xi tilde does outside that. My approximation is done inside the ball. Okay. All right. Now, this is just equal to integral Bm I mean, to begin with, you integrate on whole of Rn, but outside Bm, g is 0, xi, the function xi is also 0. That's less than equal to, take the supremum norm of g minus xi out. Once you take that out, what remains is simply the measure of Bn whole to the power 1 by p. But the supremum norm is what is precisely less than epsilon by 2. So you get epsilon by 2 mu Bn to the power 1 by p. No, not just epsilon by 2. Epsilon by 2 mu Bn to the power 1 by q. That is why that 1 by q was taken there. So 1 by p plus 1 by q. That's equal to epsilon by 2. 1 by p plus 1 by q is 1. So now norm f minus xi less than equal to norm f minus g p norm. Less than epsilon by 2 plus epsilon by 2 epsilon. So my countable dense set now the countable dense set consists of all functions which are
rational polynomial in
yes, tell.
collection of all xi, where xi is in any compact. No, sorry.
Which are restrictions of polynomials with rational coefficients. There are many adjectives here. Polynomials with rational coefficients, their restrictions. So restrictions of polynomials with rational coefficients to Bm, m equal to 1, 2, 3, etc. and 0 outside Bm. Understand the set clearly. For every m equal to 1, 2, 3, etc., consider the ball of radius m around 0. So ball of radius 1, ball of radius 2, ball of radius 3, you have only countably many. Okay. Now consider the set of all polynomials with rational coefficients. Again, you have only countably many. Set of polynomials with rational coefficients is only countable. Agreed? Now, consider those functions which are restricted. So now we have two sets. One is a set of balls, the other is a set of polynomials. Both sets are countable. Take a polynomial with rational coefficient. Restrict it to one of the sets, that is one of the balls, and put 0 outside. Fixing a ball, how many such functions will you get? Countably many, because your set of polynomials with rational coefficients is after all countably many. You are restricting each of them to Bm and putting 0 outside, you will get countably many. And you are doing this to countably many balls only. So countable product, in this case, final stage is product of two countable sets is countable. That's why. It is kind of intricate, but any argument in measure theory is like this. Okay, these are not there in Rudin, but obviously, I mean, Rudin doesn't have everything. You should know certain basic stuff. I think
Sir,
now, yeah.
This 1 plus 1 upon P plus 1 upon Q is 1, right?
Yeah, that is how Q was chosen, yes.
But then in this, there are three equations. Second equation, you will get mu of Bn also. So.
Oh, you're right. Oh, thank you. Oh, I thought that becomes 1. No.
No, so instead of your constant above, you have chosen mu of Bn 1 over Q. That you should take, I think, mu of Bn minus 1 over P.
Yeah, that was a bad choice. You're right. Thank you. Yeah. It will just cancel. I just wanted to cancel it with that. Yeah. So BM. N is for Rn, and this is BM. Yeah.
And sir, another thing was that this Ji was chosen so that infinity norm of G minus Ji is so this infinity norm you should take over the BM, right?
Over BM.
Not over the spot. Yeah.
Not yeah, over the BM.
And that's why you have to take the closed ball.
That's why you have to take the closed ball so that the supremum is finite. Okay, thank you. I thought it does not matter. But Sushil, why can it not be taken over just the support?
Sir, because when you are taking in the equation below, yeah, this
you're right.
second equation you are taking inequality.
You're right. Okay, let me explain what Sushil said. Thank you, Sushil. So I'm approximating G by Weierstrass theorem, right? Where I'm approximating G on BM. Take BM to be a closed ball. Now G is a continuous function. That's all. And so on a compact set, if you have a continuous function, you can approximate it by polynomials. So I have found a polynomial xi tilde, which approximates that. That's this equation. Now, to suit my convenience, because xi tilde cannot belong to LP if I leave it free, I cut it to 0 outside the closed ball BM. That's why the closeness will be required for Weierstrass theorem. So xi is the measurable function, which is equal to xi tilde on the closed ball BM and 0 outside. Right. Thank you, Sushil. And the supremum is right. Yeah, good. So we are done. And okay, we have 15 minutes, a little more than 15 minutes, and maybe I should finally get down to L infinity, huh? Because I haven't spoken about L infinity yet. I have been taking 1 less than equal to P less than infinity. Okay, so let L infinity be the set of all those functions. So again, a measure space, okay? I don't need the topology anymore at the moment. Functions f, of course, I mean, the topology doesn't harm, but if we want to be very general, for which the set So let L infinity the set of all those functions f for which there exists a capital M for sufficiently large M, for which there exists a capital M such that the set of all x, such that mod fx greater than M, the inverse image of the set open M infinity, and well, complex, if it's complex valued, then yeah, it's best to write this way: mod fx greater than M. This has measure 0. There exists a capital M such that the set x belonging to x satisfying mod fx bigger than M has measure 0. Has measure 0. I'm not saying that a value bigger than M, like M plus 1, cannot be taken. It can be taken, but only on a set of measures 0. Okay. Now you'll be able to show that it's a vector space. That is, I mean, scalar multiplication is not a problem. Of course, it's obvious. But if f and g satisfy this, then you will have to show that there is some number M such that mod fx plus gx is bigger than M. Use triangle inequality. Okay, so show that this is a vector space. And let norm f be the infimum of all those m's such that measure of the set where mod fx exceeds M is 0. So if M is a number which satisfies that x belonging to x such that mod fx greater than M has measure 0, then anything bigger than M also satisfies that. Okay, but some things less than M also might satisfy. So look at the smallest possible, the infimum. Again, all properties of norm will be satisfied, triangle inequality, etc. I'll show you why. I'll show you why the norm equal to 0 will imply f equal to 0. If norm f infinity is equal to 0, then what does this mean? This infimum is 0. If this infimum is 0, then mu of x in x such that for all M bigger than 0, the infimum is 0. Okay. Now look at this set. So mod fx for any x, mod fx is either 0 or bigger than 0. It's a non-negative number. Can't be anything else. It's either 0 or bigger than 0. Now this is union to mu outside. Union n equal to 1 to infinity. The set of all x such that mod fx is bigger than 0 is the union over all x such that mod fx bigger than 1 by n. When if mod fx is bigger than 0, it is bigger than some 1 by n. That's all that's being said. But all this is a union of measure 0 sets because of the first line now on the screen. The entire union is a countable union of sets with measure 0. So mu of the set where mod fx is greater than 0 is 0. And mod fx is positive only on a set of measures 0. So mod fx is equal to 0 almost everywhere. Mu almost everywhere. Anyway, so f equal to 0. F equal to 0 in the almost everywhere sense. I mean, there could be some point where it's non-zero, but those can only happen set of measures 0. Okay. So that shows that it's a normed space. Now, let us see. Yeah, let us see its completeness. So let Fn be a Cauchy sequence in L infinity. See, these are the problematic sets. For every k from this sequence fk, there will be some points where mod fkx will exceed norm fk infinity in general. There may not be any, but in general, they're likely to be. Agreed? Okay. So since that is the case, so I take this, but these are major 0 sets. Okay. Do these things for fm minus fn as well. We are in a Cauchy sequence, so we will need such quantities fm minus fn, and so collect those sets as well, and they all have measure 0 for every m and n. Throw all of them out. E is a big union. It has a union of AKs, then double union of the BMNs, but after all, a countable union of major 0 sets. So mu E is 0. Outside E, outside this set of measured 0, we have what? Mod fnx minus fmx less than equal to norm fn minus fm by definition of BMN. And that goes to 0 as n and m go to infinity by Cauchy criterion. So for every x in E complement, the complex sequence fnx is Cauchy. So let me write. It's a Cauchy sequence of just complex numbers. So they will have a limit. So give that limit a name. So the strategy is always the same. This is why I told you in the beginning to read the completeness proof of Cx for X compact, that right from there, the strategy is always the same. You get hold of a pointwise limit and then show that it's the limit in the right metric. in the Cx metric or LP metric or L infinity, whatever. I have to show that Fn goes to F in L infinity. What I'm using here is the fact is the fact that is this fact. The very first line, Fn is a Cauchy sequence, means what? Means Fn minus Fm, the infinity norm, that goes to 0. Now come down to this line. For x, as long as x is in E complement, your mod Fnx minus Fmx is dominated by norm, the infinity norm, the L infinity norm of Fn minus Fm. Uniformly for every x, you don't have to worry about it. So consequently, maybe I'm a little wrong here. Then given epsilon positive, get a large capital N, such that for m and n get a greater than capital N, we have norm of Fn minus Fm is less than epsilon. Now, that would, okay, maybe I should add one more line. Oops, sorry. So mod Fmx minus Fnx less than epsilon for all x in E complement and Nm greater than n. So given the Cauchy, by the Cauchy criterion, given a epsilon positive, get capital N, so that norm Fn minus Fm is less than epsilon for all Mn bigger than n. That's just definition of Cauchy criterion. Since E complement by definition has the property that for x belonging to E complement, mod Fx minus Fn, mod Fmx minus Fnx is less than equal to norm of Fn minus Fm. So for every x in E complement, I have mod Fmx minus Fnx is also less than epsilon, pointwise. But now look at this mod Fnx minus Fx. It's a complex number. It's a non-negative number. Now that's just the limit of mod Fmx minus Fnx, fixed x, mind you. Fixed x in E complement. As limit n goes to infinity, large M. That's less than epsilon for all small n bigger than capital N. M is anyway going to infinity. Agreed? Now that holds for every x in E complement. So take supremum over E complement. So consequently, Fn goes to F uniformly on E complement. Absolutely no problem. Set F equal to 0 on E. This E is the limit. You don't really care what happens on E. Then F is in L infinity and norm Fn minus F infinity norm goes to 0. So we have produced the limit of a Cauchy sequence. Okay, it's an hour. Let us stop here. Any question? Okay, if there are no questions, stay safe. We meet on Friday at 3:30. Bye.
Okay, thank you, sir.
Welcome.
Sir, is the class is over?
Yes, sir.
Oh, sorry.